Thanks, Mark. So I'm intending this to be an audience for people who don't really know what I'm talking about. So if you're an expert and I'm being imprecise a little bit, don't crucify me. So the first thing that I want to do is spend some time explaining what is this CDH business. And the first thing, this is actually true. I can't, if I can spell it. The CD stands for Nisnevich. And more fully, he wrote something in the 1980s called About the Completely Decomposed Topology. And for about 10 years, people referred to it as the CD topology. But, well, this being the late 80s and the political events being what they were, people decided that it would be better to call it the Nisnevich topology. And so it's been the Nisnevich topology ever since about 1995. Nevertheless, this term CDH actually comes from that era. H stands for Voevodsky. So the story there is that Voevodsky wrote his PhD thesis in the early 90s in Harvard, and he invented a topology which he called the H topology because it was good for cohomology. H is for homology, and so this combination of these two, I think, first arrived in a preprint by Suslin and Voevodsky in 1995, which didn't actually get published for about 6 years. But this is the origin of the term. And it doesn't tell you what it is, but it sort of gives you an amusing way to think for the next 60 minutes if you don't have anything else. So, okay, so first of all, when you want to think about topologies, one way to think about it, topologies, is in terms of squares, because why is from the standpoint of algebraic geometry, why is a topology interesting? A topology is interesting because it allows you to talk about cohomology with respect to that topology and get long exact sequences, and hopefully the cohomology groups can be invariants that you can study whatever else it is that you're not interested in the topology for its own sake. You're interested in measuring something else. So one way of thinking about the usual topology is that if you have two open sets U and V, whose union is X, then you can form this square. So this is open, and this is open, and here is U intersect V. And the main point of this is that if you have a cohomology theory, so I want to spell cohomology. I'm too close to the C-O-H-O-M, O-L-O-G. You have a cohomology theory H star, then you get a long exact sequence. So the cohomology of X goes to the cohomology of U plus the cohomology of V goes to the cohomology of U intersect V, back to the cohomology of X, and so on. And this is something that you should have learned either as undergraduates or graduate students. So this is the usual topology. So the Nisnevich modification of this is that you allow V to X to be a tall. And there's two equivalent conditions. The first condition is for every subvariety, Z in X, not in U, there exists Z in V, so that the map from Z tilde to Z is birational. So that means it's actually an isomorphism on an open set. There is another alternative definition, which I refer to as the Nisnevich lifting property. And what it says is that if you have a point in the sense of schemes downstairs, then there's a point upstairs in the sense of schemes, such that the residue fields are isomorphic by the natural map. So that's the more algebraic way of saying this. And the key point of all of this is that this is mostly just algebraic in nature. And so the difference between these kind of squares and these squares is not so much the fact that you allow yourself the étale covers, but the fact that the étale covers have to have this particular arithmetic condition. If you took these covers and you just took this to be étale and you forgot this condition, what you'd end up with is the étale topology. And this is just a small modification of this. Okay, now, right. So then there are other squares. And so what I want to do is think about complex varieties and remember that the word proper in topology means that the inverse image of a point is compact.
Could you tell me what étale means?
Sure, étale means covering space. So if we work over the complex numbers, which let's work over the complex numbers so that I don't have to get too crazy. Here's an example of something that you might think of. So, so this is the equation y equals x squared, and this is the x line, and this is the usual projection. And what I've done is I've taken out the point x equals a, and this is not étale because there's a problem with this point. So we have to remove this point as well to make it a covering space. And now this is an étale map, but in order to make it satisfy this condition, so u is going to be x minus the set, this particular point. And the condition would be that you need the square root of a to be in your field. So if we work over the complex numbers, you never get this arithmetic business. But if you work over a number field, this kind of arithmetic business is necessary. You need this in order that this point here has the same residue field as that. It's just a very technical thing, and really, in the larger scale of things, this Nisnevich modification really isn't so important. It's more of a technique issue than anything else. H squares. So here's a picture of a typical H square. So if I take a point on a surface and I blow it up, then the inverse image of the thing that I blew up is the exceptional fiber, and you get a square that looks like this. So these squares are proper squares, and there's something in here which is closed, and I have the inverse image, z prime, and the condition is that x prime minus z prime, so this is an open subset of x prime, and x minus z are isomorphic. So if you have that, then this is an abstract blow-up square. So these are the three squares that one works with, and now so we make a definition. CDH topology is the smallest topology. So for these squares, so let's see, set of u and v, and the set of all z and x prime are covers. Now this is an abstract Grothendieck topology, and the point of the topology is really not so much what are the open sets and what are the covers, but what are the cohomology sequences. And so if you have a cohomology theory, relative to this, you get a long exact sequence. So for example, if you're working in classical, well, neoclassical algebraic geometry, you can talk about the CDH cohomology of a sheaf. And that would be the natural home where this whole business lies. Now the main issue about this is, who cares, right? It's just a definition. So here's an example. Betty cohomology has this property. Meaning that it'll take these squares and give you long exact sequences. So how do you see this? Well, if you have a diagram like this, then depending on how you like your cohomology theories to be, this is closed in here, and so you have an excision diagram, and since the complements are isomorphic, you get a long exact sequence by excision. If you have one of these squares where this is possibly not open but a covering space, then again you have the condition is that x minus u, that's a bunch of points, and v minus the intersection, well, v minus the pullback is a bunch of points, and this Navish lifting condition tells you that they're isomorphic. Well, I think I better add that condition if I'm going to be technical, and so I think just in case I haven't said that, I'm going to allow that. Okay, so if you have a square where you have a finite covering space and it's mapping down to x, then what you can do is you can take these open sets and you can replace them, well, you can sort of replace the complement of z by something which sticks out from like a little tubular neighborhood of the complement, and you can replace u by something which is almost u, but it goes in a little ways, and then you have a closed guy and a closed guy, and their intersection, their intersections are the same, and so again you have the same excision theorem that allows you to say that Betty cohomology has this property. Okay, so what's going on here is I want to say that a cohomology, let's see, so here's another example of the same sort of a thing. Suppose I take Hochschild homology. Now, Hochschild homology is something which was invented for rings back in the 1940s by Hochschild in order to do deformations. And if you sheafify this, then you get a chain complex of sheaves, and the Hochschild. So there's an annoying thing that goes on, and that is that for some reason or another in this subject, because it started in ring theory and everything was a subscript in ring theory, people sort of decided that we were going to use subscripts. So the Hochschild homology of X would be the hypercohomology with a minus n of X of this complex. And if you work in the CDH topology, then a lot of the deformation theory that you normally see isn't there, and that everything is locally smooth. And so you have sort of, I don't know, CDH in there somewhere. This is the hypercohomology in the CDH topology of the same thing, except for, of course, here you have to sheafify these for the CDH topology. And this is a direct sum over all I of the 2I minus n, well, let's see, minus plus minus n, Zariski, of the x coefficients in omega I. If x is smooth. So if you start off with something like Hochschild homology and you play these kind of games, you get a theory for all varieties which looks like something very classical in the smooth case. So the CDH topology maps to the Zariski topology, and you just sheafify with respect to that. One can tell it concretely, but I've never seen a decent description. So for example, if you take this and you sheafify it with a CDH topology, then this is O of the semi-normalization. So to try to do this with Kaler differentials is more awkward. Okay, why do you care about this? Well, so here's an example of a covering. Suppose you take a singular variety and you stratify it. And we'll take over the complex numbers. So you find a sequence of sub-varieties so that all of the xi minus xi plus 1 are smooth. And now you take a resolution of singularities. Of each of these. So here is xi tilde to xi. And then you want a covering. Take the resolution of singularities of x. That's not quite a covering because of this condition. You have to worry about this, but you have a covering of that by x1 and a covering of that, the remainder by x2. And this is a CDH cover of the thing that you started off with. So what has happened is that anytime you have a cohomology theory, you can try to analyze the cohomology theory by looking at coverings. And here's a very nice covering. And what you see is that locally, X is smooth in the CDH topology. Started off with any singular variety, I stratified it, took a resolution of singularities, and then I got a covering, and each of the pieces of the covering is smooth. If I started off with something that was projective, and I did this, then each of these, of course, would be, each of these xi's would be projective, and so the resolution of singularities would be projective. And so it would be something that was locally smooth and projective, even, in this topology. Knowing that something is locally smooth tells you that if I'm looking at something like this, and I sheafify it for the CDH topology, then locally it's the same thing as the smooth thing, And so this is exactly what you get. So now you don't need that hypothesis. Except for, now one has to be a little bit more careful with what this means. So we have a fairly good computational tool. We know what Kaler differentials are. And we know the cohomology of Kaler differentials. And so you have a fairly good computational handle on what this is. So this is an example where passing from the Zariski topology, where working with Hochschild homology is a very technical subject. When you pass to the CDH topology, it becomes something that's much nicer and much more amenable to calculations. Okay. Well, I wanted to give some more examples of this. So if I pick an eye and I look at the ith layer of the Hodge filtration, and I look at the x's, then each of these squares give me a long exact sequence of Hodge structures, and each of these kind of squares gives me a long exact sequence of Hodge structures. And so, so this is going to fit together. So what's the general formulation of this? We say that a cohomology theory is a CDH cohomology theory, just in case it takes all of these squares to long exact sequences, and that's what these are. So here's another example, which is sort of almost tautological. If you take the CDH cohomology of some sheaf, obviously you're going to get something which is going to have long exact sequences. Now there's a modification of this. And that is, suppose F is not a sheaf. Well, what can you do that's more general than a sheaf? You can do a chain complex of sheaves or a chain complex. What's even more general than a chain complex of sheaves? Well, a chain complex of sheaves gives you a topological spectrum. So algebraic K-theory would be one of these kind of things. So if you take a variety, the algebraic K-theory of the variety can be thought of as many things, and the topological homotopy groups of this thing take K, apply X, you get some spectrum. Take the homotopy groups of that spectrum, you get something that's algebraic K-theory. So you can talk about it in this context, and you can ask if something has the CD property too. So now I want to talk about CDH descent a little bit more carefully. So we have this notion of CDH descent. And the notion of CDH descent is not exactly cohomological descent, but it's a related notion that was invented in the 1980s by, I guess, Thomason and a bunch of other people. So CDH descent, if it takes, let's do this, squares, two exact sequences. So what I've been giving you are examples of chain complexes whose associated cohomology groups are going to give you CDH descent. And now there's a universal such. In the case of sheaves or chain complexes, well, in the case of sheaves, this is given by an injective resolution.
What's F here?
Well, I was trying not to say what F is, but let me say there are two cases that I have in mind. F could be a chain complex or a sheaf, or F could be a pre-sheaf of chain complexes, a pre-sheaf of sheaves. Well, that doesn't make any sense, a sheaf. Or it could be a pre-sheaf of spectra.
So maybe you mean exact triangle instead of exact sequence.
Well, I put a star there. If you want me to remove the star, then by removing the star, I get that. But this isn't the place where we have to worry about who's the audience. So I was trying to stay a little bit more. So there's a universal map like this, and that's universal with respect to maps to theories which satisfy this descent. And for example, if you take K-theory and you apply this universal process to it, you end up with something which is called homotopy K-theory. Homotopy K-theory was something that was invented in the 1980s to solve a completely different problem. And the observation that it satisfies this is something that was done by Hasemeyer in 2003. And so I told you that the definitions of CDH topology came from the late 90s. And here in the 2003, we start seeing some sort of a connection between all of these ideas in algebraic K-theory. Previously, all of this CDH stuff had been invented by Suslin and Voevodsky in order to worry about motivic cohomology and some conjectures there. So suppose that F is a suppose that F is a pre-sheaf of spectra. These would be the homotopy groups, where I put the minus sign up here to, okay? So you get a cohomology theory. So if it takes any of these squares to distinguish triangles, well, homotopy Cartesian squares, I think is the right term, actually. If it takes any of these squares to homotopy Cartesian squares, then when you take homotopy groups, you get long exact sequences. And it's really the long exact sequences which you use for computations anyway. So if I take the spectrum, I get the homotopy Cartesian squares. If I take the cohomology theory, I get long exact sequences. Does that answer the question? So this, the definition of it is it takes X to take the K-theory of X cross a simplicial, co-simplicial space. So this is the space where the nth term is the coordinate ring of the n-simplex. And because this is contravariant, this co-simplicial variety becomes a simplicial variety. And then you take the realization of that. So that's the definition. But you see, this definition has nothing to do with what we've been talking about. It was designed to solve a universal problem of a different kind. And the universal problem that it was designed to solve is this. Okay, but as it turns out that this is not so related to what we're worrying about. Okay, so one thing that you can do with this with very little work is this. So here is k of x, here's hn of x. So this is negative cyclic homology. And just for the sake of having a concrete discussion, I'll put homotopy groups in here. The universality of this map gives me some sort of a way of thinking like this. There's a canonical way of mapping Hn into periodic cyclic homology. So this is the Dennis trace map. And this is the Chern character. And so this is more or less an observation that was made in the early 90s in a different disguise. But this observation was made by Combs and Kruby. Now, one thing that you can do if you have this, anytime you have a map, you get a long exact sequence. Or if you're thinking in terms of spectra, you get a homotopy. So let's call this thing f k of x. So it's just the third term in the long exact sequence. There is a canonical long exact, whoops. The fiber of this might be Hn. And you would also have a fiber here. And the fiber of this would be f of Hc, cyclic homology. And the big theorem from 2008 is that all of these are isomorphic. So what that means is that this theory, which has a lot of features which you might call motivic, so this behaves much more closely to a cohomology theory than algebraic K-theory does. The map from algebraic K-theory to topological K-theory, for example, factors through this thing. The Chern character here induces something like a secondary Chern character, which is landing over here. Now, if you expand out here's this f, and here's this hc, and minus 1 of x. And this is the same thing as the fiber of the map from K-theory of x to the homotopy K-theory of x. This is something which is eminently computable. This is something which you have some sort of control over. And so this thing, which is in the middle, is fairly computable in many cases. And that means that the difference between algebraic K-theory and homotopy K-theory is computable.
You almost said it on the right-hand board. It's KH and K with a subscript of CDH. Are those two things the same?
This is the CDHification, if you like that term, of this. If you don't like that term, this is the universal map from K-theory to something satisfying CDH descent. If, for example, n is negative, then cyclic homology doesn't exist if x is affine, let's say. HCN of x is equal to 0 for n less than or equal to 0. And since this term here is hcn of x, what you see is that this is an isomorphism, and so that therefore this term, which is something which is essentially computable in terms of de Rham cohomology, turns up as the third term in this sequence. So what are some of the applications of that over the last 6 years? So this is all since 2008. And most of this is joint work with a bunch of people. So one of them is Cortinius, and one of them is Schlichting. And one of them is Hasemeyer, and one of them is Walker. So the first thing that you see from this is that Kn of x, so I'm not saying it's immediate from this picture, but it's not hard once you have this picture. And that is that K-theory vanishes below, the negative K-theory vanishes below the dimension of the variety. And so this is a sort of a technical issue. If you are working with spectra, you'd like to know that your spectra are bounded below so that lots of things converge. And the fact that you do have some sort of a vanishing in negative degrees is a pretty big deal. And so this was an old conjecture which had been around since 1980. And the second thing is, so let's say the D plus first K group is the same thing as the D plus first K group of X cross affine space. And that implies that X is smooth. And that is an old conjecture which had been around since 1976. And again, it's just playing with this diagram. D is the dimension, yes. So let's let D be the dimension. These depend on the characteristic of the field, but I'm taking the complex numbers as my field just because another example of this is that we now are able to completely compute the K-theory of varieties. For example, if you're interested in the K-theory of the node, and I'm picking 3 just for some random reason. So this is K3 of the complex numbers plus K4 of the complex numbers. And of course, Dan, these would be replaced by varieties, by your favorite field. And then what's coming up next is the big surprise. And that's the Kaler differentials of the complex numbers over the rational numbers. So this calculation was done. So the node means it actually doesn't depend on the precise algebraic equation, but if you take x squared plus x cubed equals y squared, for example. So what is this Kaler differentials? So if you've never seen Kaler differentials, let me just work with this one. So it's given by generators d alpha, where alpha is in the complex numbers. It is a complex vector space. And the relations that you get are the relations of calculus. So that means that the derivative of alpha plus beta is given by one formula, and the derivative of alpha beta is given by another formula. This is a presentation of it. And it works for any field. You could replace complex numbers by any other field containing Q. And the dimension of this vector space is 2 to the L of naught. So it's huge. So at various scattered points in the literature, you find people discovering that when you do these calculations, you get something is divisible. You get that something is infinite. You get that something is uncountable. You get that something is no torsion. And they're all just reflections of the fact that there's a complex vector space sitting here in algebraic K-theory, which nobody had expected before. Now I had... Sorry? Well, okay, so the general pattern for this kind of a thing is... Well, let me give you the next one in the pattern. So K4 is K4 of the complex numbers plus K5. So you always get this. This is the KH part. And now what you get is omega squared and the complex numbers. And so then what happens here is you get the third differentials, the fourth differentials, and this gives you the first differentials, the second differentials, and so on. And then when you pop up to this one, you get a new generator. And so you get generators in each of the even degrees. And beyond that, it looks like a free algebra over the ring of Kaler differentials. So,
is K the affine line the same as K of C?
yes.
So could you explain, so I see why the K4 of C is coming in. Could you explain where these Kaler differentials from this?
The Kaler differentials are coming from this secondary. So this is the thing you're trying to compute. This is the thing that's K4 plus K5 of C. So then the third, and this splits. That's easy to see. So then this thing is the vector space. This thing is related to cyclic homology, and it's related to this CDH cyclic homology. And in negative degrees, this is the term that dominates. And in positive terms, this is the term that dominates. And the cyclic homology of simple algebraic varieties was computed back in the 80s by lots of people. And so this is the term that is actually popping up. And cyclic homology is related to Kaler differentials. Does that answer your question?
You know, a priori, the bottom row is all complex vector space. And the left four that you were just pointing out.
No, you don't. You know a priori that it's a uniquely divisible group. And the fact that it is a complex vector space revolves around various surprises having to do with where's the conductor ideal and whatnot. So one thing that happens is that these kind of calculations that I've been showing you only work for varieties where the equations are defined over the rational numbers or now algebraic number field. In general, if x is not defined over the rational numbers, or the rational numbers algebraic closure, then there's sort of a Gaussmanin connection and it's not really the Gauss-Manin connection, but it's a filtered piece of the Gauss-Manin connection. And what it does is it takes the Kaler differentials of x over the complex numbers. Well, let's say take Kaler differentials 1. And then you would go to the Kaler. Let me think about this. Yes, when you go to x over the rational numbers, you're adding more relations. And so there's a sequence which goes Kaler differentials of x over the rationals, Kaler differentials of x over the complex numbers, and the third term over here would be the Kaler differentials of the complex numbers over the rational numbers, tensored with OX. So over here, what you end up with is the first cohomology on X with coefficients in this thing. And so this turns out to be very closely related to the Gauss-Manin connection. So if things aren't defined over the rational numbers, you get this additional little fun. So part of the reason why the examples that I'm showing you are very simple is because all of their coefficients are rational numbers. So I wanted to show you one other example, which is a similar flavor, and that is this sort of a thing basically uses the fact that the normalization of this variety is finite over it and smooth. And so because of that, the CDH square that you're worrying about is this one. So this is a finite map, therefore it's a proper map. If I remove this point and I remove those 2 points, then this is the square that comes up in the CDH, and so you have a long exact sequence for this. This is the K-theory of a point. This is the K-theory of a point because of the affine line. This is the K-theory of 2 points. These maps are the diagonal inclusion, so one factor comes around, and that's the extra factor that you get. So this is just nothing more than the fact that the normalization is finite and smooth over it. But if I take the cone of the plane conic, so this is just supposed to be fancy language, but it's the thing that's given in 3 space by the equation xy equals to z squared. So if you take the cone point and you blow it up, then you have a copy of the projective line, and what you end up with here is a vector bundle over the cone, and here you have a point. So your square that you're working with has very nice terms. The term that you want to know, these are basically going to be the same except for the business about the vector bundle, and that's just the K-theory of a point. So for example, there's a copy of the complex numbers sitting inside of K1 of x. And the way that that works is if I take 1 minus alpha z, alpha x, alpha y, 1 plus alpha z. Now, the determinant of this is 1 minus alpha squared z squared. And then there's a minus, so I think probably I need a minus sign on one of these. So the complex number alpha corresponds to the class of this particular matrix in X. So you can actually make things very, very concrete. Before we had these calculations, what we knew is sort of like an ad hoc basis. Given alpha, you could construct this matrix, but you didn't know whether it was trivial or not, whether it was elementary or not. And now we know not only is this elementary, not elementary, but we know the complete obstruction. And if I take K2,
When you take the class of that automorphism of that,
this is an automorphism.
bundle. Or no,
This is an element in GL2. So X is a speck of a ring, right? So let me put the ring down, okay? GL2 of R, and it gives you an element in K1 of R, which is the general linear group of R made abelian. So a 2 by 2 matrix gives you a arbitrary matrix. The class of this matrix is the thing in K-theory. K2, here you have the Kaler differentials of the complex numbers over the rational numbers again. And if you go to K3, then you get omega squared plus a new generator and so on. So we have a complete calculation of the K-theory of these kind of varieties. One thing that I find sort of amusing in all of this is that if we think about the periodic cyclic homology, for example, there is a decomposition given by certain operators which some people refer to as Hodge operations, and some people refer to as lambda operations, and other people refer to as Adams operations. But the point is that there are lots of operations, and these particular groups break up into simultaneous eigenspaces in this way. And if X is smooth, then the periodic cyclic homology of X is isomorphic to the 2I minus nth de Rham cohomology of X over the complex numbers. And so, because you have CDH descent, if I say that X is projective, then the periodic cyclic homology of this has to be the same thing as the Betti cohomology. So if X is smooth and projective, then the negative cyclic homology, which intervenes in these Chern classes, is the I plus first layer in the Hodge filtration. Because why? Because it's, well, because it's the cohomology on X of the Kaler differentials less than or equal to I plus 1. And greater than I. And this breaks up as a direct sum of things. So HQ x omega p, where p is greater than I, and p plus q equals 2I minus n. Because we have this nice stratification of any projective variety, and we have this resolution, that means that if I put the CDH in there, HN, CDH, I don't know where to put the CDH anymore. So now for any projective variety x, we have essentially the same decomposition. The Chern classes that I was telling you about, if I put an I here, and I put an I here, I can put an I here, and I can put an I here. And what it tells you is that the Chern classes are going to take K-theory, and they're going to land in this piece of the Hodge filtration, which gives you sort of a simple explanation of something which has been fairly complicated over these years. So the point is that we have this topology. It was originally designed for looking at motivic cohomology, but by trying to apply it to other areas, we get lots of new insights to things. We get ability to compute lots of things. And I think it's all very exciting, and thank you very much.